In today's video, we shall look at review problems associated with electromagnetic waves. Problem 1. In a region of free space, vacuum that is, the magnetic field at an instant of time is given by that expression. The unit here is microtesla. And the electric field is given by that vector expression, and the electric field is quantified in the unit of newtons per coulomb. Part A, show that the two fields are perpendicular to each other, and Part B, determine the pointing vector for these fields. What we have here is an EM wave, and in an EM wave, the electric field and the magnetic field, they fluctuate with time. They are functions of time. At any time t, these two fields will always be perpendicular with each other. In this problem, what we are given is the expression for the magnetic field and electric field at a particular time. And we want to show that these two fields are perpendicular to each other. The best way to do this is to take the dot product of these two vectors and show that the dot product vanishes. We know that dot product of two vectors are given by the following expression. The magnitude of E in this case times the magnitude of B times cosine of the angle in between them. If the angle between them is 90 degrees, namely if they are perpendicular to each other, then the dot product should be 0. Let's see if that is the case here. Your electric field is given by 0.2 I hat plus 0.08 j hat plus 0.29 k hat. And we want to dot this vector with the B vector, which is 80 I hat plus 32 j hat minus 64 k hat. Now, being microtesla, so there is a common factor of 10 to the power minus 6 outside. Well, this doesn't matter actually in this case, because this is just an overall factor within that dot product. So let's do the dot product. First, I with I, so 0.2 times 80, you get 16. And then j with j, 0.08 times 32, you get plus 2.56. And finally, k and k, so 0.29 times minus 64, which will give you minus 18.56. Now you can write the overall factor if you want, and you see indeed that is 0, showing that E dot B is in fact 0, meaning the two fields are indeed perpendicular to each other. Now let's do part B. Determine the pointing vector for these fields. The expression for pointing vector, as we have seen, is given by the following expression. 1 over mu naught. Mu naught refers to permeability of free space or vacuum, times the cross product of the electric field and magnetic field. So let's express this cross product in determinant form. So I, j, and k. So the first row will be the components of the electric field. So the coefficient of the I hat, or the x component of this field, is 0.2. The y component is 0.08, and the z component is 0.29. Now let's look at the magnetic field. The x component is 80 times 10 to the power minus 6. We can write that 10 to the power minus 6 outside. The y component is 32, and the z component is minus 64. So let's calculate the x component by crossing out I hat in two mutually perpendicular directions. So this times this minus this times that. So for the x component, you have minus 14.4. Now let's do the j, or the y component. The minus is from the formula itself. So crossing out the j in these two directions and taking this times this minus that times that, you get minus 36. And finally, for the z component, again you cross the k into mutually perpendicular direction. This times this minus that times that, you will get 0. Now let's not forget the overall term, 10 to the power minus 6 over mu naught, that appears here and here. Since the value of mu naught is 4 pi times 10 to the power minus 7, the final answer is minus 11.46 I plus 28.65 J, the unit of watts per meter squared. And that's the pointing vector for these fields. And that solves the problem. Problem 2. Figure below shows a plane electromagnetic sinusoidal wave propagating in the x direction. So the direction of propagation of this wave is that way. Suppose that the wavelength is 60 meters. The electric field vibrates in the xy plane. So that is as shown by this blue wiggly line. And the amplitude of this electric field is 25 volts per meter. Calculate first the frequency of the wave. We know that speed of a wave is given by frequency times wavelength. So if you want to determine the frequency, it is the speed, in this case the speed of the electromagnetic wave in vacuum, over the wavelength. So let's assume this wave is propagating in vacuum. Speed of light in vacuum, or speed of electromagnetic wave in vacuum, is 3 times 10 to the power 8 meter per second. The wavelength is given to be 60 meters. So the frequency is expressed in the units of hertz, which will give you 5 times 10 to the power 6 hertz. We can even proceed to determine the angular frequency, which is given as 2 pi, the frequency in hertz, and that's going to be 3.14 times 10 to the power 7 radiant per second. For future use, let's also calculate the wave number. Wave number equals 2 pi over wavelength. We know what the wavelength is. It's 60 meters, so 2 pi over 60 per meter. That is the unit for the wave number. Or quite simply 0.105 per meter. Now let's do part B. Find the magnitude and direction of the magnetic field when the electric field has its maximum value in the negative y direction. You see that when the electric field is in the negative y direction, the magnetic field is in the negative z direction. So the direction of that magnetic field at that point is minus k. Since the amplitude, because we are talking about maximum value, so that is the amplitude of these fields. The amplitude of the electric field is given as the speed of light times the amplitude of the magnetic field. So the magnitude of the magnetic field there is the magnitude of the electric field there over the speed of light. So you get minus k, E naught is 25. That is the amplitude for the electric field. C is 3 times 10 to the power 8. And in terms of vector notation is minus 8.333 3 times 10 to the power minus 8 K Tesla. K shows the direction of the magnetic field is along the negative z-axis. Now part C. At that instant, write an expression for the magnetic field with the correct unit vector with the numerical values for B naught, K, and omega, and with its magnitude in the form of that. So the vector B at that instant has a direction of minus K hat, as been worked out in part B, so minus K hat. The amplitude is 8.333 times 10 to the power minus 8 Tesla, so that's B naught. Cosine K is the wave number, and omega is the angular frequency. So omega is 3.14 times 10 to the power 7 T minus K 0.105x. And that solves the problem. And of course this is a magnetic field, so the unit is Tesla. Thank you for watching.